Welcome to the second tutorial of Unmixing Science about the Sediment fingerprinting technique. In this video, we will specifically focus on how to properly use unmixing models, the useful tools inside the FingerPro package, and some dos and don'ts that'll help you move in the right direction when using the technique and the different models. In the previous video, it was explained the basics of the technique, its utilities, and how to use it. So, if you are not familiarized with the technique, just go and check the previous video and come back later. In this tutorial, unlike the previous one, I will explain to you the tools and also how to fully implement the technique with the open source software FingerPro with code examples. In this video, we will go from the basics of how to install the FingerPro package in art to the most novel techniques out there such as the CI, CR and CTS methods. Let us begin by shortly introducing the package we will be using during this short tutorial. FingerPro is an open-source R package in which users have all the necessary tools to correctly implement the fingerprinting technique, and contrary to other models, the package keeps being updated with every new technique developed by the fingerprinting community. We could structure the R package into three main blocks. The first block is composed of all the graphical tools that help users to understand their data, source discrimination, and check for anomalies or outliers. A second one is composed of all the tracer selection functions, to remove the non-conservative tracers, select those that better discriminate your sources and deeply understand your dataset, and finally, the unmixing model and how to interpret its results. Let's start with the first block of functions. If we go to the previous video, we would find a series of 2D and 3D plots included in the package to quickly visualize our data, going from box splits, linear discrimination graphs in 2D and 3D, PCA and correlation plots. Most functions included in the package could be divided into first, the data input, second, the tracers we want to display, and finally a variety of Boolean to specify the type of plot and its representation. Before taking a closer look at these functions, a nice tip to follow in introducing your data is to always follow the data structure of the examples already included in the package. Now, let us take a closer look at these functions. To see this more clearly, let's check all the functionalities by installing the package on our computer. Either using an IDE such as RStudio or Base R, the following steps are exactly the same. To proceed with the installation of the package, first, open RStudio. I would recommend using RStudio because I think is quite handy. Its purpose is very simple. It makes working with R easier and is also open access. When you open up RStudio, you'll get this one window that has several panels in it. On the one to left we have the script window. This is where we do out actual programming. The next thing to do is to open a blank R script to be able to save our codes instead of just running them in the console. The one used here, it will be saved after the tutorial and shared with all of you in the description section below the video. Thus, you can follow the tutorial running the code if you want. Well, let's introduce the first pieces of code and run them. The first and second things to do are install and load the package. We install the package by writing and running install packages, FingerPro. To run the pieces of code we are writing, you can go and click the run button at the upper part after locating the cursor in the line code, or by default, pressing Ctrl-Enter, depending on your computer, your internet speed, and how many of the packages used by FingerPro have you already installed on your computer. It will take from seconds to a few minutes. Now that the package is installed, let's load it by introducing the following code, library, FingerPro, and run it. Loading the package will give us access to its help file. To access the help section, we need to introduce the name of the package, including a question mark before it. In the panel on the right, it will appear the help section. If we take a look, there are some tips in the example code, such as the description of the dataset or what each function does. Let's begin by loading the example dataset and running the different plot functions. First, the box plot will help us understand our dataset by visualizing the different concentrations of each tracer versus the mixture sample. The arguments for these functions are all described in the manual, but can also be visualized with the help function as before. The main utility of the box splits is to compare your individual sources' data with your mixture data. If we run the function and click the zoom button in the plots window, we will visualize the 6 first tracers divided by sources and the mixtures. As a more sophisticated type of plot, we have the correlation plot that displays a correlation matrix of each tracer, divided by the different sources and also includes the number of samples in box splits. Some authors have also used this graph, also known as biplot, as the tracer selection method to discard those tracers out of the source's range as a more restrictive test than the traditional range test, but we will go into that later. Finally, the package includes two more graphs that are usually used to check the discrimination capacity of the tracer to the sources. The LDA plot function performs a linear discriminate analysis and visualizes the data in the relevant dimensions, either in 2D or 3D. Besides, by changing the Boolean text to true, we will be able to see which samples are furthest from their sources and think about why. For example, in the catchment dataset, we can see how by selecting the first 10 tracers, the plot suggests an overlap between the two sources pi and pi1, and it could be wise to merge them after looking in more detail at the data. In addition, a PCA graph can also be displayed to help us with the data interpretation. By running the next line of the code, we will merge both sources. Now if we rerun the LDA plot, our sources display better discrimination. This is just a mere example of how we could interpret our real data. However, as can be seen in the bibliography, additional plots such as cluster analysis or expert knowledge could be used when merging your sources. In a second block, we are going to dive a little bit into more complex methods for tracer selection and data interpretation. However, before moving to these new methods, let's check why they are needed. Traditionally, when implementing the technique, different tracer selection methodologies have been proposed, being the most extended three-step method composed by the range test, the Kruskal-Wallis test, and a discriminate function analysis. In addition to these previous ones, the mixing polygon has been also widely implemented. However, as once they were the state-of-the-art, nowadays they are considered obsolete techniques. Recent research highlight how non-conservative and erroneous tracers can be incorporated in the models when using these methods, and modify the results of both frequentist and Bayesian models. These researches evidence that traditional tracer selection methods can no longer be used when implementing the technique, and that either frequentist or Bayesian models have problems dealing with erroneous tracers. For this reason, no further studies use these methods when implementing the technique. However, the functions for implementing them are still included in the package, but with a warning message. So, if we cannot trust in the previously implemented methods, and both types of models are affected by erroneous or non-conservative tracers, what can we do? No worries, as ones were proved obsolete, more advanced methods were developed, such as the CI, the CR, and the CTS, to which we will take a look in this video. Beginning with the CI method. One of the multiple advantages of this new method is that it allows us to guess the unmixing results, even before unmixing, and displays the information of each individual tracer, such as those of the figure. Basically, the function quantifies all the possible predictions for each tracer. Now, let's work with the second dataset stored in the package. If we run these code lines, we will load the dataset, extract the prediction, and plot them in ternary diagrams. Here, we display the first 8 tracers' individual results. In addition, to complement this information, the same function that generates the predictions displays the conservative index, in which lower values represent the lower conservative behavior of the tracer. Now that we understand what the function does, let's see its utilities and how we could even guess the model solution by just looking at the individual predictions in the triangles. If we put them together, it's evident that their predictions cut each other in a point. We could guess a sediment source contribution of around 60% for source 1, 10% for source 2, and 30% for source 3. Now, let's run the unmixing model with just these 2 tracers. As we can see, the results are in the range of our estimations. However, with the inclusion of several tracers, and especially those with no consistent information or out of consensus, this process starts to complicate, but we will go there later. In the same research that the CI method was presented, the authors also realized of the existence of conservative tracers that transmit erroneous information to the models, even in controlled environments such as artificial samples. In the figure, we can see highlighted 3 tracers that are not crossing the theoretical solution, ergo, introducing erroneous information to the model despite their apparent conservative behavior. To prevent this, the consensus ranking or CR method was developed. The notion of consensus can be illustrated with the following example: a ternary graph representing 3 sources, with all the individual results of 4 tracers. All the tracers present line patterns and apparent conservative behavior. However, only 3 intersect in a small area, while the 4th tracer has different intersections with each of the other 3 tracers. The CR method is implemented by combining the predictions of single tracer models in several random debates. For example, for 3 potential sources, 4 random tracers are needed. In each debate, several rounds are played, excluding 1 tracer at a time. The consensus of each round is measured through the mathematical compatibility of the system of equations. The tracer whose exclusion produces a higher consensus is marked as dissenting. Repeating this process through several debates, each tracer obtains a number of participations and a number of lost debates. In this image, we can see the results of the CR approach for the artificial sample, and how the method was able to identify problematic tracers that remain distant from the theoretical solution. Further information about these 2 methods can be found in its original research paper. Now let's run the code to calculate the CR from the previous dataset. Depending on the number of rounds, it will take more or less time. The output will be a table with all the tracers and their respective CR scores ranging from 0 to 100, with higher numbers representing higher consensus. Once we have all this information, we could see additional concerns didn't explore before. For example, if you look at the triangles, you can see that the combination of different conservative tracers could give different consensual and conservative solutions. Finally, during the development of these 2 methods, it was discovered the existence of multiple conservative, consensual, and consistent solutions. Thus, in order to individually identify and extract all those different consistent and conservative solutions, the CTS was developed. But why is this method needed? If your dataset has multiple solutions and you introduce tracers that pinpoint to these different solutions together, your model could choose to go for one of them or just fall in the middle. However, the major concern here is that you never realize the existence of the multiple solutions or why your model chose between one and not the other. To avoid the use of the technique and the models as a black box, all these methods were developed to be implemented before unmixing and produce comparable unmixing results when implemented in different models. For this reason, the CTS method was created. Briefly explained, this method extracts all the consistent solutions inside each dataset, displays them, and selects those with highest consensus and conservative behavior to help both models and users create more defined solutions. With this information, researchers could apply their expertise and background knowledge to interpret the possible solutions and select which is more likely in their study area. I know it sounds a little bit complex, but as with the previous methods, an example would help with its understanding, and we'll see that it's much easier than it looks. If we run the code lines for the CTS, first, we will extract all the possible pairs or triplets depending on our number of sources. After this step, we increase the number of tracers for each of these pairs or triplets, with those that produce consistent, discriminate, and consensual solutions inside the dataset. Once we have obtained this info, we can unmix the different groups of tracers and extract the different solutions existing in our dataset. Here we did only the first 2 solutions, but you can loop over the function and extract as many as you want. However, remember that the pairs or triplets are ordered based on their consistency and discrimination capacity. Thus, as further we go from the first row, less discriminate our tracers will be. Now, let us summarize what we have learned in this video. 1. The tracer selection is one of the most crucial parts of the unmixing procedure. 2. When correctly selecting the tracers, different types of models give equivalent solutions. 3. All types of models are affected by erroneous tracers. 4. By implementing the CI, CR, and CTS, users not only obtain conservative, consensual, and consistent solutions, but they increase the understanding of their data. 5. Revealing the multiple solutions in each dataset opens the door for catchment expertise implementation. 6. CI, CR, and CTS implementation avoid the use of models as a black box. I hope you enjoyed the video. Feel free at any point to comment in that section below the video for doubts or suggestions. You can contact me by using the following email or learn more about FingerPro on GitHub. In the next video, we will specifically focus on how to use isotopic tracers in the different models, the most implemented techniques to deal with them, and the new method developed for their use together with the most commonly used tracers. Don't forget to visit the repository, and if you enjoyed the video, please give us a like and subscribe to the channel.